We are live now. Yeah, Krishnan, you want to start?
Okay, sure. So it's a great pleasure to introduce Dr. Jaban from NISER Bhubaneshwar. Known him for a long time, especially since the time he was doing his PhD from HRI. But after that, he has done postdocs from Queens and even a long Inspire Fellowship in ISC Bangalore. So yeah, great pleasure to have him here. He'll speak on modular forms and certain congruences. Over to you, Jaban.
Thank you very much, Krishnan. So, and also thank you to all the organizers for inviting me. So I was at home actually. So, and then now I am in quarantine because this is the rule at NISER. When you come, you have to be in 7 days quarantine. So I am at home. So I have still not gone to the offices after coming back. Okay. So the title of my talk is Modular Forms and Certain Congruences. So we'll do in a very basic level. We'll see, and then how modular forms and what are the congruences people have studied. Certain kind of congruences I'll talk about, and then we'll talk about more that what is certain kind of Ramanujan congruences we'll study more, and then the non-existence of Ramanujan type of congruences that we'll see in this talk. Okay, so we begin with the partition function. So Pn is the partition function. It is the number of partitions of n. So this is very famous function, and Ramanujan has studied more on partition function, and one of the Ramanujan's results on partition function is these following congruences. So P5n plus 4 is congruent to 0 mod 5, P7n plus 5 is congruent to 0 mod 7, and P11n plus 6 is congruent to 0 mod 11. So, and Ramanujan also says that looks like that there is no other prime for which these kind of congruences are true. Okay, this is only for 5, 7, 11. And this kind means like this is 5n plus 4. This kind of means like Pn plus C kind of. So C is mod 5 or something like that. Okay, so this means this is true for all n, for all integer n, non-negative integer. Of course, means like P0, 1 you can say. So all non-negative integer or all n bigger than equal to 0, these congruences are true. So Ramanujan proved that. And in 2003 actually, so Algren and Boylan, they proved that there is no other prime. In fact, they proved whatever the Ramanujan predicted, that there is no other prime for which these kind of congruences are true. So this is invention paper 2003. Okay, so the above congruences have relation to the theory of modular forms. So we'll come to what is the relation of these congruences with the theory of modular forms. So let us start doing modular forms, and then I'll come back to these kind of congruences. Okay, so when you start modular form, then this is a very group, starting group, you need to study this group SL2G. So SL2G is the set of all 2 by 2 matrices with integer entries and determinant 1. And another thing which you also study is the complex upper half plane. So H is the complex upper half plane. And SL2G, this group acts on this space of this upper half plane in this way. ABCD Z is AZ plus B plus CZ plus D. Now we come to the definition of a modular form. So a modular form of weight k. So when you say a modular form, so modular form has certain, so here we are taking integer, so we just say that modular form has certain integer attached to that, that is called the weight of the modular form. And when you say modular form, generally in broader sense, you have a group and you have a space kind of thing. So here in our case, it is SL2G is that group and H is the space. So SL2G acts on H. This kind of things are there when you in general you define something automorphic functions. But our case is very simple. The starting one, that SL2G is the group and H is our space. And modular form means modular form. Whenever you say modular form, so there is a non-negative integer attached to it. We'll just take non-negative. There are also negative, but we are just concentrating on modular form, so it's non-negative. So here we have group SL2G. So the definition is modular form of weight k on the group SL2G is a function f from H to C, complex valued function. So first property is that it is analytic on that upper half plane. Second is this property, that transformation property it has. So this is called modular property. So f Az plus b by Cz plus d. Notice that earlier slide I said that SL2G act on H the way A B C D Z is Az plus b by Cz plus d. So in particular, Az plus b by Cz plus d is again an element in the upper half plane. So f Az plus b by Cz plus d is Cz plus d power k fj for any matrix A B C D in SL2G and any element in the upper half plane Z. This is the second condition, and we have the third condition, that it has this kind of expansion. So this is called the Fourier expansion of a modular form. So fz has this kind of expansion, summation a n q power n. Generally people write q power n, where q is e power 2 pi I j. Okay, so this is the definition of a modular form of weight k on SL2G. So we'll see in later part of my talk that will actually change the group. You can change the group, change the space, but in our case, in this talk, what we'll do is that we'll change the group, and still we can define a modular form in a similar way. We'll come to that, what kind of group we are interested in. So this is the definition of a modular form. So modular form is three properties. It is analytic on the upper half plane. It has some property, this transformation property, which is called the modular property. And the third one is that it has Fourier expansion starting from 0. It has non-negative exponent. Okay. So when A0 is 0, the constant term is 0, then we say that F is a cusp form. So we will not come to this cusp form. We are not going to use much in this talk. And we have the space MK. MK means if you collect the set of modular forms, all modular forms of weight k on SL2G, then it forms a finite dimensional complex vector space. So that we denote by MK. And for a ring which is a subset of C, we denote by MKR this set of modular forms of weight k on SL2G again with all the Fourier coefficients in R. So this AN are called the Fourier coefficient. So this is called the Fourier expansion of a modular form FZ, this Fourier expansion, and AN are called the Fourier coefficient. So for a ring R, if the Fourier coefficients are in some ring which is subring of C, of course, because the Fourier coefficients are in C, from the definition one can see that they are in C. But if for a particular subring, if we take, and then if all belong to that particular ring, then we just denote that set MKR. This is the set of modular forms. We collect the set of modular forms of weight k on SL2G such that all the Fourier coefficients in R. So that set is MKR. Okay, and let us come to some examples of modular forms. So this is generally again whenever you first study modular form, these kind of examples come first. So ek, so ek is 1 minus 2k by bk summation sigma k minus 1 n q power n. So again, q is e to the power 2 pi z, bk is the kth Bernoulli number, and sigma k minus 1, it is defined in this way. So sigma k in general, you can one has the definition. So in this case, we have sigma k minus 1. So here we define for any even integer k bigger than equal to 2, and this is called the Eisenstein series. So this is Eisenstein series, and this is a modular form if k is bigger than equal to 4. If k is bigger than equal to 4, then ek is a modular form of weight k. That is why k is written here. So this is weight k on SL2G. Okay, if k is bigger than equal to 4. But note that here I have said that for any even integer. So this is what I want to say, that ek is in mk if k is bigger than equal to 4, and E2 is not a modular form. So E2 is not a modular form, it is a quasi-modular form, and we'll not also discuss about quasi-modular form in this talk, but E2 has very important role. Although it will not come in my talk, but the theory, which is the mod P theory of modular form, E2 plays a very important role in that theory. So, but it will not come in my talk because it is behind, means like whatever the results, etc. E2 is involved in all those results. Okay, and then one important result is that this is the thing. If you in particular, you can say that any modular form is a polynomial in E4 and E6. So here ek is defined for any even integer bigger than equal to 2, k bigger than equal to 2, and here this property, this statement says that any modular form is written as can be written as a polynomial in E4 and E6. So these are basic things generally one does when one studies a first course in modular form. Okay, so now with this, now we define we in this talk always p means p is always bigger than equal to 5 and it is a prime. So unless I tell something else, p will always denote by this p is always a prime which is bigger than equal to 5. Okay, so ZP is the local ring, so it is well known. So it is A by B, where A, B are integers and GCD of A, B is 1. So in fact, any rational number you can write like this, but here one more condition is this, that P does not divide B. So denominator is not divisible by P. So this is ZP, this is a local ring, and so its unique maximal ideal is PZP. Okay. So ZP, if you see, that is a subring of C. That is a subring of C, and MKZP by the previous definition, if you notice, MKR is the set of all modular forms with set of all modular forms which all Fourier coefficients are in that ring R. So here this R is ZP, and this is a result which one can prove without much difficulty that any this says that, means like the previous statement which I said here also, any modular form with coefficient with all the Fourier coefficients in ZP can be written as a polynomial in E4 and E6 with coefficients in ZP. So when you write the polynomial in E4, E6, that coefficient is in ZP. So earlier it was everything was C, so I didn't say anything, but here this is one result, but one can prove it without much difficulty. So for this proof, I think that one can see many things, but I think Lang book one can see that this proof is there. Okay, so now since we want to study the congruences, so generally we study congruences between integers, but here we study congruences when the elements are in ZP. Okay, because this way we are kind of generalizing the congruences. We only study means high school level you study congruences when you say that A is congruent to B mod M something, then you assume that A, B are integers. But here we can generalize it because Z is inside ZP. Z is inside ZP and we are generalizing it. That means we are kind of studying congruences for more general class, not only for integers. And here is the definition. We have suppose two modular forms may be of different weights. We have two modular forms may be of different weights, and we say that modular forms are congruent mod P. So here the all the Fourier coefficients are in ZP. As I said, coefficients are in ZP. Then we say that F is congruent to G mod P. That means the two modular forms are congruent to G mod P if each coefficients are congruent mod PZP. Okay, so An is congruent to Bn mod PZP for all n. So then we say that F is congruent to G mod P. Okay, so now we have some examples. So P bigger than equal to 5, then one can see that like with because of the properties of Bernoulli number, etc. E2 anyway, E2 is all the coefficients are in Z, so we do not have any problem. EP minus 1 and EP plus 1 have all the Fourier coefficients in ZP. Okay. And also we have the following thing, that EP minus 1 is congruent to 1 mod P. So here note that means like I'm talking about EP minus 1. This is a modular form of weight P minus 1. And 1, this is constant modular form, 1, just 1. So I'm talking about these two modular forms are congruent. Okay. So this is the so that means it's a one is Fourier exponent just 1, that constant term, other there is no other term, other terms are 0, and EP minus 1 already I have defined EK. So in particular you can define EP minus 1. So this is congruent to 1 mod P. And second one is EP plus 1. Again, this is a modular form. E2, that this is not a modular form, but what you can do is when you say congruences between modular forms, I define, but in fact you can talk about congruences between two Q series. That means if you have a Fourier expansion like the modular form, even if you do not know whether they are modular forms or not, you can talk about if the coefficients are in ZP, you can talk about the congruences, whether these two Q series are congruent or not. So this is what I have in the third example. If you see that EP plus 1 I have written, although E2 is not a modular form, you can still talk about the congruences. So that is why I have written here. Okay, so these are some examples, and it was the result of Swinnerton-Dyer lecture notes in mathematics, Springer lecture notes in mathematics, 1972. So he proved that if you have two modular forms, then if they are congruent mod P, so none of them are congruent to 0 mod P, and if F is congruent to G mod P, then K is congruent to K prime mod P minus 1. That means if two modular forms are congruent, then the weight are certain way related. You cannot have arbitrary weight. Okay, so weights are related. So K is congruent to K prime mod P minus 1. So this is very, and this is the starting point of mod P theory of modular form. And then we Swinnerton-Dyer and Sayre further developed the mod P, and there is a whole very deep theory now. People are use various algebraic geometric, now the Hida theory, etc. There are many branches have come, but this was the starting point. This was the starting point of the mod P theory of modular form. Okay, so now, so this is the first result. So now we state some more results, and then we'll see what are the relation. So for this, we define that Fp is this field of P elements. And what we do, so we have taken modular forms with coefficient in ZP. So for a modular form, any modular form, we have a Fourier expansion with suppose the coefficients are in ZP. So you can go modulo P ZP. Okay, that means go modulo P ZP means you have a Q series, and then you make it P modulo P ZP, each coefficient mod P ZP. So then this AN bar, this is what AN bar. You make it mod P ZP. So coefficients are in ZP, then go modulo P ZP. So then these coefficients are in FP. So now you have a Q series expansion. So now you forget about whether this will nothing to do with modular form. If you have modular form, just you go modulo this, and then this is a Q series expansion, you can say, with coefficients in FP. Okay. Okay. So this is one. This will be very useful. Again, we'll see this. And Gxy, suppose this is polynomial in xy, two variable x and y with coefficients in ZP. So why I am doing this, it will be clear that why I am defining all this. And for a modular form, if a Q series is given, this is the reduction. And if a polynomial is given over ZP, you can again you can reduce it. Again, you reduce modulo reduce the coefficient modulo PZP again. So this is the way. So again, if you reduce, so this is the notation G bar xy, and this if you reduce, the coefficients will be n bar. So again, this will be in FP xy. And MZP, so you collect the all modular forms with coefficients in ZP. Okay, all modular forms on SL2G with coefficients in ZP. Okay, this is graded ring. So this is the graded ring of all modular forms on SL2G. And now, so this is the result. I'll come to this. But what is MFP? So when you have modular forms MZP, this is the collection, and then each modular form you have Fourier expansion. You reduce this Fourier expansion mod PZP. Okay, then what you get a set of Q series expansions with the Fourier expansion or Q the coefficient Q coefficient or the Fourier coefficients will be from FP. Okay, so that is MFP. So you have MZP, and then for each modular, it is a modular form, and then or you can say that it is a Q series expansion, and you go modulo PZP. So then the coefficients will be in FP. So that is MFP. Okay, and this is the very first result in this mod P theory. That can you give a description of that this FP algebra, MFP. So this is FP algebra. This will be FP algebra. So MFP, can you give a description, proper or known description? And this is what Schwinnert and Dyer proved again in the same paper, that lecture notes, Springer lecture notes, that there is a ring isomorphism between FP and this A bar xy minus 1. This is the ideal generated by A bar xy minus 1. What is A bar xy? So we know that this any modular form can be written as polynomial in E4 E6, and also we know that any modular form with coefficients in ZP can be written as polynomial in E4 E6 with coefficients in ZP. So E P minus 1, I said that this has coefficients in ZP. So you can write it as polynomial in E4 E6. So A E4 E6, whatever that polynomial, AXY is that polynomial, such that if you evaluate E4 E6, that will give you EP minus 1. Okay, so and that is again ZPXY. It will be like that. One can see that. Okay, so this is A E4 E6. So once you have AXY, then you reduce. This is a polynomial in XY. Then you reduce the coefficient modulo P. That is what A bar XY. Okay, then it is again it is an element in FP XY, and this is the ideal generated by A bar XY minus 1. Okay, so this is the this is very starting result in this direction, giving a description, because if you reduce modulo p, if you look at MFP, there is possibility. In fact, there are we have seen that EP minus 1 is congruent to 1 mod p. So that means whenever EP minus 1 comes, then you reduce modulo p, then you get 1. So there may be many Q series expansion, they will be same. And then we know that what is the relation. If they are same, that means weights are related by k is congruent to k prime mod p minus 1. So that is why. So many things will collapse. Kind of many things will be same, and then this gives a nice description of how it looks like MFP. Okay, so this was the result, and this result has been generalized to modular forms of higher level. So let me talk something about higher level. So for higher levels, actually means that we define modular forms for certain kind of subgroups. So these kind of subgroups generally people consider for arithmetic purpose. So this is gamma n. Gamma n is a subgroup of SL2G satisfying these conditions. Gamma 1n again satisfying this condition, and gamma 0n with satisfying these conditions. All these are subgroups of SL2G. And higher level means you consider modular forms over any of these groups where n is bigger than 1. Why n is bigger than 1? Because if you look at, if you take n equal to 1, then you get SL2G. Everything will be SL2G. So when you, so there is a definition of how to define modular forms for these kind of groups. In fact, more generally finite index subgroups of SL2G, but we are not defining here. But for our purpose, mainly what we want is that Fourier expansion, because we want to study congruences. So in the, when you have modular forms over these, so you have a Fourier expansion the way I described in the case of SL2G. So higher level means n is bigger than, so any of these groups you consider, and then n is bigger than 1, then you say that modular forms of higher level. So what are those results? So Catch actually did it for gamma n, where n is bigger than equal to 3, and Gross also did it for gamma 1n, where n is bigger than equal to 4. And mostly, generally, the idea of Swinnerton dier, you cannot, the way Swinnerton dier does, it cannot be generalized to any n, because there are some specific properties of SL2G which are used in the theory or whatever Swinnerton dier has proved. And the proof actually of Cage and Gross, generally they use algebraic geometry, mostly algebraic geometry they use to get similar results what the Swinnerton dier proved for SL2G. So in what we have done, so in a joint work with Sujit Kumar Singh, so he's my former PhD student. So we generalize this to modular forms on gamma 02, because our aim was that nobody was considering level 2. So Cage did it for 3 bigger than equal to 3 and Gross bigger than equal to 4. So we're looking at gamma 02, and then we're hoping that kind of SL2G, whatever the way Swinnerton did, possibly it can be done for gamma 02, because we are just in a small, this is gamma 02, it almost behaves like SL2G in certain way. So that is why we wanted to do it for this level 2. And then we have proved similar result. For this, actually, what results we have proved? For this, we need to define these kinds of Eisenstein series in the case of gamma 02. So EK2 is defined in this way. EK is defined modular form on SL2G. So similarly, EK2 one can define in this way. This is the definition of EK2 for K even bigger than equal to 4. And E22 is defined in this way. So note that E2 is not a modular form. But when you take this linear combination, this becomes a modular form. So each even k bigger than equal to 2, EK2 is a modular form of weight k on gamma 02. Okay, one can, so this is very not very difficult to check that these are modular forms on gamma 02. Okay, so the way we define for SL2G, similarly we can define the graded ring. That means you collect the all modular forms of all weight, and then the coefficients are in ZP. So the graded ring I'm saying, so direct sum of all this with coefficients in ZP. And again, in a similar way, you can define the FP algebra. So that means what you do is that Q series expansion you have, then you reduce modulo PZP, and then you get Q series with coefficients in FP. Okay, so this is M gamma 0 to FP. So this is our result. So this is accepted. So this is, that is a question mark whether it will come 21 or 22, we do not know. So here note that here the Swinnerton result was there for p bigger than equal to 5, and in this case we are able to do it for 3 also. And the reason is that we do not have in SL2G case, we do not have modular forms of weight 2, and here we have, this is weight 2 modular form in gamma 0 2. So that is why we are able to do it for p equal to 3 also. And here similar ring isomorphism we have proved in a similar way. So p bigger than equal to 5, same thing whatever the polynomial, because in this case I should have mentioned here that the role of E4 E6 is played by E22 and E42 in this case. Like the polynomial, any modular form can be written as E4 polynomial in E4 and E6 in case of SL2G. And here similarly in this case modular forms over on gamma 0 2, any modular form can be written as polynomial in E22 and E42. And similarly with coefficients in ZP also, whatever I have stated for SL2G, similarly you can do for gamma 0 2. Here the modular forms will be E22 and E42. Okay, so these are the like similarities between SL2G and gamma 0 2. So that we could proceed with some technical difficulty, but little, not more. Okay, so this is the result, analogous result which we have proved. And now let us again come back to the congruences which we started with, that these kind of congruences studied by Ramanujan, then one can define what is called a Ramanujan type congruence. So Ramanujan type congruence means you have a Lorentz series. You can also say that start with negative also for some negative, finitely many negative terms also is fine. So it said to so we have a Lorentz series is said to have a simple congruence. We say that either this is simple congruence or Ramanujan type congruence, because these are the type of congruences. So Ramanujan type congruences at C modulo P. Okay, if A Pn plus C is congruent to 0 mod P for all n. So that means if the all the coefficient in certain class Pn plus C, okay, like here 5n plus 4. So here 5 is appearing and then 5n plus 4. So we say that if you are given a series, nothing to do with modular form, you just have a series like this, and then you can say that it has simple congruence. In some paper they write simple congruence, and in some paper they write Ramanujan type congruence. So that is why I have written both. Either you say it's simple congruence or Ramanujan type congruence. So at C modulo P, if A Pn plus C is congruent to 0 mod P for all n. Okay, so that means if you consider this series Pn Qn, so the Ramanujan congruences are nothing but the simple congruences associated to this series. Okay, and another thing is that this Pn, this series actually is related to modular form. So this is not what I have defined. So this is related to certain, you can say, half integral modular form. This is relation to eta eta function. So whatever I have defined modular form, it is not exactly that, but it has certain transformation property. This is kind of although this is the expansion, and then it has relation with eta product. So I have I do not want to go into that, but it has some relation with modular form. And the proof of the 2003 paper proof that Algren and Boylan, they use whatever the theory I said, the Swinnerton diad, they use in a certain way to prove that there does not exist any the congruences which Ramanujan studied for other primes other than 5, 7, 11. Okay, so this is the result of Michael Dewar. So he used the theory, mod P theory, to prove the non-existence of Ramanujan type congruence or simple congruence for these kinds of modular forms. Although means E2 is not a modular form, so but you can always change E2 by EP plus 1, because we have said that in the example which I gave, that EP plus 1 is congruent to E2 mod P. Okay, and then in place of E2 you can just write EP plus 1, and then same things, same whatever the statements will be true, because we are studying congruences. So that is why I just said that this kind of modular forms, that E2 power R, E4 power 6, E4 is 6 power T. So here R S T are integer and R is non-negative integer. So not all are 0. So if everything is 0, then you just get 1. So it boils down to the trivial case. So that is why. So here he proved that using the theory of mod P modular form. So whatever the theory of Swinnerton diad, that is called mod P modular form, theory of mod P modular form. So he proved that for so if there is a simple congruence at C, that means P has to satisfy this. That means if P is bigger than this number, because once you have RST fixed, that means this is a fixed number. So if P is bigger than that, then you cannot have simple congruence or Ramanujan type congruence for that P. Okay, and if you look at this proof of Algren, and they have kind of used this kind of argument, that as I said, that the mod P modular form they have used, and they have just fixed modular form here. If you look at, they have fixed modular form. So that means once you have fixed modular form, then you can in fact go something more, and then you can in fact say more that for these kind of primes you will have only congruence, and other kind of prime you do not have the congruences. And in fact in their case, they could determine that 5, 7, 11, you know that the congruences are there, for other you do not have congruences. But since here we are varying RST, it can be anything, so we are giving that which prime, for which primes you do not have congruence at least. But if you just fix RST, possibly I haven't done it, but I think you can in fact determine that exactly for which prime you will have congruence and for which prime you will not have congruence, because so there are certain ways of doing, like something called storm bound, etc. one can use, and then see whether congruences are there or not. And then for other prime you can because for finite you need to check only for finitely many prime, because for P bigger than this there is no congruence, and for less than that you need to check. But because for less than these numbers, there it may happen that for some prime you get congruence, for some prime you do not get congruence. So the Michael Dewar actually he used the mod P theory, and which was known, Swinnerton diad. This is mod P theory, SL2G mod P theory. Swinnerton diad, what he did, so he used the mod P theory for modular function SL2G and proved that E2 power R, E4 power 6, E6 power T, if you have this Q series expansion, and if it has a Ramanujan type congruence at C mod P, then P has to be less than or equal to this number. And what we have done, because gamma 02 was not there, so we first that proved various results on mod P theory on gamma 02, and we proved a similar result where the modular forms which we have taken is r e to power r e2 to power s e4 to power t. As I said that e4 e6 are replaced by e22 and e42 respectively in this case gamma 02. So similar, going in a similar way, whatever Michael Duer has proved for SL2G, we were able to prove that we have we proved the non-existence of Ramanujan type congruences for certain p. Okay, so this is what we have proved. I have not got into details of this proof, but proof involves again some more deep theory of the mod p modular forms. Okay, so I think I am done. Thank you.
Thanks, Jaban. That was very nice. And
yeah, I finished, I think maybe before something. 40 minutes it took.
That's fine. We have a lot of time for questions.
Yeah.
So may I ask if the audience has any questions or comments?
Yeah, thank you very much for this very nice talk. I would like to know a bit of your proof techniques. Actually, I'm not read your paper. I'm sorry.
Yeah, no, it's okay.
But if you can just comment on that, like.
Yeah. So first thing is that the whatever the Swinnerton dial have proved, we have proved that. So there are certain how I'll say. So okay. So we use more deep theory in mod p modular form like filtration, etc. So like here we say that k is when two modular forms are congruent, then the relation is that k is congruent to k prime. So if the weights are k and k prime, so k is congruent to k prime mod p minus 1. So there is certain term which is called the filtration. Filtration means the smallest weight for which for a Q series you take, and then you find out modular form of smallest weight. Okay, smallest weight such that that is congruent, that Q series is congruent. So once you have filtration, so there are certain results on filtration actually. So there are certain results on filtration, and those kind of, and then theory of filtration also is there. So little bit. So those kind of things we use in this proof. So yeah, but detail I do not know how to tell actually. But the things which we use that mostly mod p, and then that filtration we use mostly filtration, and then various types of results involved in where filtration is involved.
Thank you.
Hi, Jaban.
Yeah.
Thanks for the nice talk. What I wanted to ask was, so except for gamma 02, then this is not done for any other congruence approach.
I think it is done for certain level, like half integral. So Michael Duer, he has another paper. So where he has done for gamma 14 or gamma 04, and where he does modular forms of half integral way, or something like theta, the modular forms involving theta or eta. So these kind of things, this is, I do not know the exact year, but Canadian Journal of Mathematics, this paper, so which he has done. So I do not have for which level it has been done, which level it has not been done. It is I do not have any idea. But what we wanted was that we just wanted to prove that description of for mod p modular form, how it looks like for gamma 02, like the Swinnerton dial proved the isomorphism. And then after that we look for some application, if we can give some application of that. And that is why we proved that we saw, okay, this application is there, so we did. So, but I exactly do not know for which prime, which level it is done, this kind of congruences.
I have a question. Thanks
Yeah.
thanks for your nice talk.
Thank
I am curious if you fix a prime number p
Yes.
and you look at the set of integers n, such the partition is congruent to 0 modulo this prime. Is it always infinite this set or not?
You are saying that you fix a prime.
Yes, for example, 7, 10 or 31 or so. And you look at the which number n such that Pn is congruent to 0 modulo this prime P. Because if you look at only the arithmetical progression, this simple congruence maybe not. And now, if you look at not only for all n, you look at for which n, and you want to estimate this set. Is it always infinite or not?
Yeah, there are some results. I do not know exactly what results. Actually, in the same paper, Algren and Boylan, they have proved some result relating to that actually. So, but something I do not know exactly what exact statement or is that, but I feel that they have some result. Actually, this partition function people have studied more, so I have not gone into what all the things are, but I think there are certain results. There are certain results.
Because I feel if you use the Eisenstein series and so on, you get maybe only the simple congruence and so on. Maybe you because it's strong. If you have congruence on the modular form, you have a strong congruence. Maybe. Yes, I don't know. Is it possible to get something from that? Maybe
yeah,
not.
but I don't know whether you can use this theory because so what you are looking at, so mostly the way we are doing is that congruence for each coefficient actually, and then the way we get a pn plus c actually the way is that we get a modular form where if you have a q series expansion like related to modular form, like in this case e4 e2 power r, e4 power s, e6 power t we are taking. So and we are saying that it has simple congruence. Simple congruence means a pn plus c, you have congruence at pn plus c. So this is related to have a modular form where the all coefficients are congruent to 0 mod p. Okay, this is a certain way actually you can do this. And but you are saying the opposite one, that how many n you can get, but I doubt whether using this theory you can get that.
Okay, thank you.
May I ask another question?
Yes.
Okay, so what about cusp forms? Is this theory also applicable there? Or?
Yeah. I mean, like this, whatever this theory is for all modular forms. Okay, all modular forms. If you look at the Swinnerton, it does not say about cusp form, modular form. Everything you are taking that in the that FP algebra, you are taking everything. Okay, so there is nothing distinction here. Cusp form or modular form, nothing. You take any modular form, it will work.
No, so I meant like the result of your types, like
yes. This again, as I said, that Michael Duer has proved it for that eta function. Okay. So when you say eta function, so that is a kind of cusp form. So some particular level he has considered gamma 1 4 or gamma 0 4. I do not remember.
Because the ring will be generated by So
he has again he has proved similar kind of results. Swinnerton Dyer or something like that. In that case, half integral or and then congruences he has studied. So I think he has done it for certain cusp forms also he has done.
Okay, thank you.
Okay, if there are no further questions, let's thank the speaker again. Thank you, Jaban, for the
Thank
great
you
talk.
very much for inviting.